Okay, so we're going to start section 9.2, waves at media boundaries. I'm going to apologize in advance. This is a little bit longer of a lesson, and there's lots of little things to go through. None of it's super taxing, but you may have to pause and reread or listen to things a few times just to really have it go in. So let's get started. I'm just going to grab my highlighter here so we can pick off a couple of the key pieces in this text. So wave speeds depend on some of the properties of the medium through which the wave is traveling. We've talked a little bit about that. So the speed of sound, for example, depends on air temperature. The speed of a wave along a rope or on a guitar string depends on the density and tension of that rope or string. So what we haven't talked about yet is what happens when the medium changes. So everything so far we've had one medium. So what happens to a wave when it moves down a rope and encounters a different medium such as air or a wall or something along that lines? What happens when you're above water yelling at someone and they're underneath the water? Can they hear you? What happens to the sound? Okay, so those types of things, that's where waves interact at something called a media boundary, and that's where the change in the medium is. Okay, and they can take on a whole bunch of different forms. We're going to explore a couple different variations, and the two easiest ones are going to be free end reflections or fixed end reflections. They're going to be very similar. And then we're going to also look at something called a free end to a fixed end reflection, but we'll go through all of that in a minute. So let's just start with free end reflections. So the easiest way to think about a free end reflection is that there's nothing holding one end of the rope back. And we'll talk about ropes just because it's easy to visualize. So as you can see in this picture here, you send a wave down. This end right here, this is the free end. It's allowed to move. So it can wiggle and jump around. A flag is a great example of what a free end reflection could look like. So what we see is this wave comes down, it gets to the free end, the amplitude matches up, and then the wave actually reflects and goes back along the top side or the side it came down on. This is a really important distinction because you're going to see something different when we look at other types of reflections. So for a free end reflection, okay, the wave will go back along the same side of the medium that it came down at. Okay, that's a really important idea. Okay, now a fixed end reflection, and this is one we're more familiar with. You've seen it with slinkies. And I'll do one shortly with some slinkies to show some of this. This is one end is not allowed to move. So this is your fixed end. That means no matter what happens, that medium has to come to that point. Okay, so if you send a pulse down along the top here, as it gets to the wall, okay, it's going to interact with the wall or whatever's holding it in place in this particular example. And then because of Newton's third law, which we know is the equal and opposite, action reaction. Okay, so that medium applies a force, say, upward. The wall applies a force downward of the same magnitude. So what we see is that that wave actually goes back along the bottom side. So if we're thinking of our free end reflections, the pulse went back along the same side it came down. On fixed end reflections, it goes back on the opposite side. Okay, so if you look here, there's a couple of short videos in the PDFs. I'm not going to bring them all out inside this video, but I will go to the PhET simulation because it's really good and it helps you see. You can also do these if you want to get an extension cord or something out at home or some rope. You can try playing with this. So the first one we'll model is a fixed end. Now this is a fun little demonstration because you can do this with your mouse. I'm going to turn dampening off. Dampening is just the loss of energy or loss of, I can think of it like friction for a wave, so I'm just going to turn that down for now. So I'm going to send one pulse down. Okay, now because this is a fixed end, you can see the pulse comes down and it goes back along the opposite side. The wrench over here represents another fixed end, okay, so that the pulse keeps flipping back and forth. Okay, I'm going to change to a loose end. So this could be something like a ring on a pole. So now if I do the exact same thing, you see that the reflection, okay, when it's at the free end, comes back along the same side. When it hits this fixed end, which is the wrench, it flips over. Okay, now again, you can start this. You can play with some different things. You can change the tension, and you'll notice something really different with the tension. Okay, it's a little easier to watch what happens to all of the little beads that make up the string. It goes back and it comes back along the same side. Okay, so that's one way you can see your fixed or your fixed free. They called it a loose end. Doesn't matter. And if you're just curious, no end just means we send this off into space. Okay, and away it goes. Okay, now if we wanted to, let's just try one more here. I'm going to send, whoops, let's restart that. I'm going to send one pulse up here, one pulse down here, and we should see that idea of constructive and destructive interference. See, there was one really big wave there. Okay, and that's something we're going to explore a little bit more in the future. Okay, so now media boundaries. We're going to call something called faster medium, and you can just think of it as like a thick rope being tied to a shoelace. Okay, that would be one way you could think of a fast medium. Something, and I have it kind of scrolled down here a little bit. A fast medium, let's get the highlighter out. So a fast medium, you have stronger particle connection strength. That's one way of thinking about it. So something, and then slow medium, lower particle connection strength. That's the only way I could really think of describing that. So when you have a fast medium, so say a thick rope going to a shoestring. Okay, so that shoestring, and sometimes you think of this as density as 2, but be careful with that. As that medium connects here, as the pulse comes along the fast medium to the slower medium, that slower medium can be thrown about really easily. So it acts like a free end. So what you see is that the pulse continues down the new medium, but the pulse also reflects back along the same side it came down on. And what's really important to take away from that is that if this had a height of 2, then both of these would have to be some combination to get to 2. They could be 1 and 1, they could be 1.5 and 0.5, whatever it might be. Now, you could also have something like a shoelace attached to a thick rope, where this faster medium acts like a fixed end. So as you send your pulse down, some energy will be transferred into the faster medium, but some will also be reflected back, but it'll be reflected back on the opposite side. Okay, and once again, if this had an amplitude of 2, then you would expect this to be 1 and 1, okay, in terms of their magnitude. Which leads us to something called standing waves. So now standing waves, when we send a pulse down, and maybe I'll go back to the PhET simulation in a minute, when you send a pulse down or a string and then it reflects, you get interference if you send multiple pulses down. And when you get the right frequency, what can happen is the interference of the waves can be both constructive and destructive, but when you align them perfectly, you get something called standing waves where the crests are standing on top of the reflected crests. Okay, and everything starts to jump in its amplitude. So I will do that with Slinky shortly. But we have these two new words to define. Whoops, that's not what I want. I want a highlighter. Node is one, and antinode is the other. So a node is a location where the particles of the medium are at rest. And this is really fascinating because when I do this with a Slinky in a minute, you will literally see the Slinky at that point does not move. So these are nodes. Antinode is the location where the amplitude is twice as big. Okay, so they're the highest or furthest parts. Okay, so you can see inside here there's a blue wave. That's the original wave. And then as it hits a medium and reflects back, this amplitude, oops, that's not what I want, this pen right here. So this one, if we were to draw a line, this has an amplitude of 1. When it interacts with its reflected wave, this becomes an amplitude of 2. Okay, just for discussion's purpose for numbers. Okay, so now we're going to continue working with 2 fixed ends. It's the easiest one to see, but we're just going to define a little bit more notation. So we have something called the fundamental frequency, also sometimes called the first harmonic, and it's also going to be tied with something we're going to call n equals 1 for the fundamental. Okay, you can, if you're into music and you want to watch some harmonics or read more about harmonics, you're welcome to. We're not going to talk much about overtones, and what you'll see with overtones is they're just one off in their numbers, but we're going to stick with just harmonic or the fundamental frequency because it's a little easier to follow. So I'm going to do a little slinky demo here, and you can watch that, and I'll go through a bunch of terms, and then we'll come back and carry on this conversation. Okay, here goes nothing. So this line here in the middle represents equilibrium. I will be moving my hand between this board and this board, so the amplitude of the spring will be quite literally one floorboard. But what you'll see is when I hit the right frequency, you'll see this spring will jump out to 2 boards away for amplitude, and that means I've hit a standing wave. So we'll go for the first harmonic, which should be half a wavelength. There it is. So that's half a wavelength. Okay, and you can see my hand is not moving outside of those floorboards, yet the spring is going a long way past. Okay, if I change that now and I go a little quicker, you can see I now have second harmonic. I have 1 full wavelength, and again my amplitude is going well past where my hand is moving. Let's do third harmonic. This is a little trickier. Okay, so you'll notice something's happening. The frequency should be going up. Okay, and there's an actual number value here that's predictable with this, and that's what standing waves in a fixed spring system look like in real time. Okay, so as you saw in the Slinky demo, we saw a couple of different shapes. And again, so this is our number of nodes between the ends. So you'll see there are no nodes. It's just an antinode. We call this our first harmonic or our fundamental overtone. So we said we are not going to worry about overtones. I'm just going to call this first, and that's all I'm going to talk about. So this is n equals 1 right here. Next one would be our second harmonic. So this is n equals 2. Third harmonic, n equals 3. Fourth, n equals 4. Make sense? Okay, now what you should see is we start to see the number of nodes increases. There's some mathematical patterns here. Okay, so when this is, get back to my pen, when this is n equals 1, there are no antinodes. When this is n equals, sorry, there's one antinode. When this is n equals 2, there are 2 antinodes. When this is n equals 3, there are 3 antinodes. Okay, it doesn't matter whether you show the top or bottom, they're just alternating back and forth. And when this is n equals 4, there are 4 antinodes. So if someone said the 6th harmonic, you would expect there to be 6 antinodes. And if you start to notice, there's a connection here. If we change to here, if we go back to the first one, when n equals 1, there were no nodes in between. When n equals 2 for the second harmonic, there was 1 node. So what you start to see is that this column right here is 1 less than the harmonic. And we don't count the ones on the ends because we're just talking about fixed ends for this particular case. Okay? All right. So now, I'm going to draw this proof. Pause it often if you need to. Bear with me, because if you can understand this little drawing, it makes where the formulas come from makes so much more sense. So if I looked at a fixed case, and we're going to start with n equals 1, so this will be n equals 1. Okay, so a fixed case, what that means is I have to start at the red dot and end at the red dot. The little blue lines will represent the maximum amplitude that I can go. So I would have this is my shape. Okay, so I have to start at that red dot and finish at that red dot, and you'll notice this is half a wavelength. If I go to free, that means I have to start, and we model this as being free, that it can go to the blue lines, top or bottom. I just model them all starting at the top. So if I draw that picture, you will notice that again is half a wavelength. Okay, so these are the standing wave shapes for each of the harmonics we'll go through, for up to like 4, I think. Okay, and this is what the standing waves would look like for these 3 different end scenarios. Okay, so now if I do a fixed free, that means I have to start here and finish up here. Now this one's a little different. You might notice this is actually a quarter of a wavelength. Okay, so let's move down, and now we'll do n equals 2. I'll change colors so we can make it a little easier to see. So n equals 2. So this is the second harmonic. So now if I do fixed, I have to go up. That would be the first right there. And now I come back. And you'll notice now I have 1 full wavelength. Okay, if I look at free, I have to go all the way down. Well, there's the first, but I have to finish at a new free. Oh, look at that. That's 1 wavelength. Okay, if I do fixed free, I go up to the top and then finish down low, and you'll say, well, hey, that's 3/4 of a wavelength. Hope you might start seeing a bit of a pattern here, but we'll do a couple more just to sort of help. Okay, so now next one, n equals 3. So that means I have 3 antinodes, 3 high points or low points. So now there's the first full wavelength, and then we finish there. So this is 3/2, or 1.5 wavelengths. If I do free, so let's try that again. I'm going to start high. Come on. Go up. And then come back down. Okay, and this will take a second, but that also is 3/2, or 1.5 wavelengths. All right, fixed free, not doing too bad here. So we started high, low, high. Okay, so this one's set up right. So now we're going to go up, down, up, and here. And now if we count that up, it might be a little trickier to see. That's 1 full wavelength plus 1/4 more. That's 5/4 wavelengths. Starting to see the pattern. Okay, let's do 1 or 2 more. Let's make sure I can get them all set up right. Let's go to red. Oh, maybe not red. Let's go back to purple. So now this is n equals 4. Okay, so now I gotta go up, down, up, down, and up. And if we count, there are 4 antinodes, which we expected, and we have 2 lambda. Okay, if we do free, and this one, see, I got this one wrong. Good thing I checked. This dot should be up high. And we'll sketch that one off. Okay, and let's go back to, what was I doing? Purple. So now we have to go low, high, low, high. Okay, and you'll notice that is how much of a wavelength? That is 1, 2 full wavelengths. Okay, and then lastly, fixed free. Make sure we're high, low, high, low. Okay, good. Drawing set up right. This is really tricky to do while you're recording, just so we're all clear on that. And then let's chop this up. So there's 1 full wavelength, and then 3/4 of the next wavelength. So this is 1 3/4, or 7/4 of a wavelength. Okay, so now hopefully you're starting to see there is a predictable pattern here. If you need to, pause, go back, rewatch it, go through it again, because to me, this being able to draw these pictures is the key piece into seeing where the formulas come from. And because all of these can be defined by a formula, they look like this. Okay, so this is for media with fixed ends or free ends. So let's just jump back here for a minute. You'll notice that fixed, and free had all of the same outputs for all of the different ends. Okay, it was only the fixed free combination that output or did something a little different. Okay, so when we're looking at this formula, the length of the medium, that's what capital L is. Please make a big note of that because lots of people mess that up. L is the length of the medium. Okay, it is not the wavelength. It's the length of the string or whatever medium you're working with, normally strings for us. Okay, please highlight that. Lambda, that's the wavelength. Okay, they are not the same thing. Okay, so n is the number of the harmonic that we're going to be dealing with. Okay, and then you'll notice, but if we put in these numbers, 1, 2, 3 for n's, we would have ended up with half lambda, 1 lambda, 3 over 2, and then 2 lambdas. Okay, so that's a pretty straightforward equation to work with. This one down here is where some people start to have some more difficulties. Again, the L is the length of the medium. Okay, so if they said you have a 60 centimeter string, that is the length of the medium. Okay, now 2n minus 1, this top part, when you substitute in n's, if we put n equals 1 into here first, 2 times 1 is 2, minus 1 would get me back down to 1. So my first harmonic would be at 1/4 lambda. And if you go back to here, that's exactly what it was. Okay, if you put in n equals 2 in that equation, it'll output 3/4 lambda. So if you put a 2 in here, 2 times 2 is 4, minus 1 is 3, 3/4 lambda. Okay, so those formula will always be provided. Your job is to know what the L, the N, and the lambda are. Okay. If you're a musician and you want to just take a quick read, this is kind of a fun little exercise. If you are playing an instrument that's considered free, you have one wavelength that looks something like this. If you put a mute or a bell on the end, something like this trumpet over here, then you change it from free to free fixed. Okay, and what happens is you actually shorten the wavelength. Okay, and I'll let you read that, but what's important to note from that is if you shorten the wavelength, okay, so if this number here goes down, okay, because this velocity of sound is constant, okay, so if you shorten the wavelength, then you have to increase the frequency so that you keep that constant velocity. Okay, so those are important little ideas to come up with or to play with if you're a musician. So let's try a few problems really quickly here. And I'm mostly going to highlight some of the terms so that we know what we're talking about. The speed of a wave on a string with a fixed end and a free end. So right away, that's an important piece because it tells me what formula I need to use. Okay, so we have a velocity of 300 meters per second. We have a frequency of 200 hertz. What length? Okay, right here, this is the big piece. What length of string is necessary? That's telling me find L. Okay, so these are the words you have to go over. So this is our universal wave equation. This is our relationship for a fixed free end reflection. I'm just going to move that highlighter out of there. Okay, so now we have to combine those things or bring them together. And this happens quite a bit. So let's write in what we know. And oops, I missed this too. There, oops. And I missed the n value. So this is also important. The first harmonic. So that means n equals 1. Okay, so if we set this up, notice the way we write this. L1, that tells you you're looking for the length of the first harmonic. Okay, so 2 times 1 minus 1. I'm going to put all that in a square bracket all over 4. Now lambda we don't know, but we do know velocity and frequency. So we could take off to the side, we could take that relationship, put 350 over 200, and I'll grab my calculator that's hiding over here. 350 divided by 200, 1.75 meters. Keep an eye on that. So I get a 1.75 here. Okay, so now I have 1/4 times 1.75. Let's bring that down a little bit. So 0.438, let's say, and that'll be meters. So this is the length of string required. So we could say 43.8 centimeters if you wanted. This is the length of string required to create the first harmonic, okay, at this frequency of 200 hertz. So that means from here to here is 43.8. It's a fixed free, so it looks something like that. It's 1/4 of a wavelength, and that's what we're doing. Okay, next one, the 6th harmonic. So right away that tells me something. N equals 6 of a 65 centimeter guitar string. Okay, so that right there's a lot of information told. The length of the guitar string is 65 centimeters. So I'm going to do a couple things. I'm going to write that as L. That length of the guitar string is fixed. It doesn't change. Okay, that's our medium. Okay, this is also going to be their 6th harmonic. I've noticed I've also changed it to meters. That's another big one. You can't work in centimeters with this. Okay, the speed of the sound in the string, so we have a wave speed of 206 meters per second. What is the frequency of the standing wave? Now there's something that's not written here. This is a guitar string. They expect you to know this is a fixed. Okay, because a guitar string has two ends that are fastened together. So this is a fixed scenario. So that's where they get that equation from. Okay, so we're trying to find frequency. So if we start with this expression here, L6 equals, back that up for a second, L6 equals n lambda over 2. If we fill in what we know, the length of the guitar string is 65 centimeters or 0.65 meters. We know n is 6. We know we have to divide by 2, and lambda I can actually replace with, we'll rearrange our expression here. Lambda can be replaced with velocity over frequency. Okay, so then I can put in velocity, put a little arrow over to that guy. Velocity is 206. Frequency is on the bottom. Might need to do a little bit of fun math here, so let's just get our calculator going. So 6 times 206 divided by 2. So my top number is 618. F is still on the bottom. If I rearrange that equation, hopefully I'm not too late at night here to make too many mistakes. I'm sure I'll be told if I do. I get 950 hertz is my frequency. Cool. Okay, so I'm not going to do all of these. Pause the video here. You can try them if you like. I'll try and do them in a separate video because I'm wary of time. So pause it, have a look, and then I'll just erase them. Okay, so welcome back. I'm just going to reveal them all so you can pause them and check your answers. They're also in the textbook. I'll try and do these in a separate video. Okay, so our summary, we have two formulas that are new to us. Okay, and I'm not going to reread all that. You can pause it, look at it yourself. And then section 9.2, 1567. Thanks for tuning in. I know that was a long one. Appreciate it.